Is that actually recording? Good. Okay. So amusingly, I was over ambitious. I was originally going to plan 3 acts for today, of which both of these sections were going to be Act 1, and then we were going to do inverse functions and other stuff. But then I realized that this takes way too much time to talk about. So we will go more slowly because I think these are interesting and spend a lot of time on these 2 sections. So you will recall we differentiated sine before. So the derivative of sine we found was cosine. We should be complete and differentiate sine. Then I'm going to talk about second derivatives. So you can take a derivative of a function that gives you a new function, and then you can differentiate that new function to get what's called the second derivative. And then something which is probably useful for your context, we'll apply this to a particular potential used in molecular chemistry, or I guess quantum chemistry. I'm not sure exactly what the right word for it is. Then we'll spend some time talking about e to the x and see why e is such an important number. Okay. First thing, we should review all of the rules for derivatives that are...
Give me a second, because reason.
Okay. I can still hear. Is that what you're asking?
Sorry about that. Mason was asking a question.
Oh no. Was he asking for more protein powder in his Gatorade or something?
No, just methods of softening PVC.
Equally strange. Okay.
Because making LARP weapons.
Oh yes, buffers. Good. Okay, that makes sense. Sweet. Okay, so this is our arsenal so far. These are the tools we have for attacking derivatives. So we found that the derivative is linear, so we use this, for instance, to solve that HMMT problem where there was a sum, the math competition problem where there was the sum of the x to the first up to x to 100 and stuff. So we used linearity to split the derivative of a sum into a sum of derivatives, so that's good. We proved the product rule, so you remember we did this by explicitly using the limit definition and adding 1 in a particular place to split the 2 limits and get the derivative of a product is this kind of sum where the derivative falls onto one term or one factor at a time. We found the quotient rule by first getting this rule for 1 over g and then using the product rule. We proved the power rule by induction. I've been slowly building up in the daily challenges to having you prove this with the binomial theorem, which we saw yesterday or whenever that was, 2 days ago. So we proved this in particular for integers, positive and negative integers. That's all so far. And then last time, this has not been proved, so I still owe you a proof of this, but we introduced the chain rule, so there should be an asterisk in your head that this still needs to be proved if you want to take it seriously. So we'll, I think, use all of these today at some point, or maybe not the quotient rule, but all of them are certainly important at some point. So you should, if you do not have them memorized or if you don't have mnemonics in your head for how to call these up at a moment's notice, it's good to have. Thoughts or questions on the derivative rules review?
I do not have any thoughts or questions. Out of curiosity, do you hear anything now?
Now I hear "wah" in the background.
Yes, that's a blow dryer.
I mean, it's not that distracting, so you don't need to do push to talk or anything. Cool. Okay, let's do the first part. So, cosine second derivatives.
Before we go any further,
Yes.
why do we? Oh wait, I was about to ask why do we need to do second derivatives if a derivative is a straight line, but that doesn't make sense because it can be not a straight line.
Yeah, good question. So you would say the first derivative. So here's the function f. If the function f is a straight line, what you're observing is that the first derivative of that function f prime is a constant, and as we saw, the derivative of a constant is 0. So if you differentiate a line twice, you'll always get f double prime equals 0. But then as you immediately realized halfway through that sentence, you know that there are functions besides lines. So say a parabola is going to have, if this is f, then the derivative of f itself is a line, so maybe it looks like this. And then that's the first derivative. Then the second derivative of the parabola, which is the first derivative of the line, is now down to a constant, f double prime, and then f triple prime will be 0. So in general, the higher and higher you make the order of your polynomial, if you start with like x to the power 100, now you can take 100 derivatives before you get down to a constant. And there are other functions besides polynomials, obviously, sine and cosine, for instance. You can take infinitely many derivatives and never get back to a constant. So, good question. But we do need second derivatives for non-simple functions, non-lines, for instance. Good. Is that what you were asking, or did I just go too ham on that?
That is what I was asking. I have another question.
Good.
It probably helps if we get to second derivatives before I start asking tons of questions about them. But is the height of f double prime above 0 how much we need to subtract from f single prime to get a tangent line?
Is the height of f double prime the thing we need to subtract from f single prime to get what again?
A tangent line.
Oh, no, no, no. Good.
Okay, so that was just super far off.
Yeah, it's a good guess though. You would expect that f double prime is somehow related to the tangent line of the tangent line, right? So I see you were trying to put together the pieces and come up with an interpretation. It's not quite right. Actually, we'll see this in chapter 4 actually. So chapter 3 is just about computing derivatives. Chapter 4 is about the interpretation and use of derivatives. But we'll see that the second derivative has a very natural interpretation as the difference between the value of the function at a point and the average value near that point. So what do I mean by that? I mean, for this blue parabola, if I go to a point like down here, and I say, okay, how different is the value of f at this point from the value at nearby points? So I go a point a little bit to the left, a little bit to the right, and say, okay, the average value at nearby points is higher than the value at this point itself. That means the second derivative is positive. Second derivative is positive if the average value near the point is bigger than the value at the point. What if we had an upside down parabola? An upside down parabola, well, if I go to a point like here, and I say, okay, what's the difference between the value at the point and average value nearby? Well, I go to two nearby points, left and right, take the average, and then subtract from this thing, and I say, okay, well now the value at this point is larger than the average at nearby points. So the difference between the average and the value is negative, so here f double prime will be less than 0. So you can also interpret it in terms of tangent lines, which is what you were trying to do, but I think this is a more natural geometric interpretation. The second derivative tells you measure how much the value at the point differs from the average value at nearby points, left and right. Good. That's just a preview, though. I will explain that. I will actually prove that. Right now I'm just saying words at you. I will actually prove that, so you should not believe it necessarily until chapter 4. But this is a preview of why the second derivative will be useful.
Okay.
Good. I like these questions. Other questions?
I have no questions.
Okay. Onward. Not awkward. All right, since you have no questions, I will ask a question to you then. So suppose f of x is cosine of x, and we wish to take the derivative, so we want to find f prime of x. What is the definition of the derivative f prime at some point a in the reals for this function?
So I believe that we are going to have I think cosine of x, cosine of a plus h minus cosine of a all over h.
Good, so that's the difference quotient, and then what? What do I do with h?
Yes, the limit of that as a zero as h equal to 0. How did I forget? Lovely.
You had a secant line moment. Good, yeah, so this is the difference quotient. Take h to 0 at the end, take the limit. Okay, so hopefully red flags are going off in your brain immediately when you see an expression like this. What do you want to do deep in your gut when you see an expression involving the cosine of a sum?
Are we going to apply the cosine angle addition formula that I can't remember?
Yes, thankfully I remember it, even though you proved it on consolidation document 1 and in the tutorial, but I will remember it for you. So Remember, the cosine one is the one where it's the gay one. It has the same flavors go together in the pair. So the two cosines and the two sines go together. So it's cosine A cosine H minus sine A sine H, not sinh, damn it, sine H, sorry, minus cosine of A all over H. Okay, so I don't know if you can quite see what we should do next, but is there a simplification that stands out to you when you look at this expression?
It's a long shot, but are you multiplying by cos A, cos H minus sine A, sine H?
Multiplying by cos A, cos... Oh, so you
Nah,
want to multiply
just
top.
make it super complicated.
Yeah, we would have to FOIL out the top if we did that. So uh, the goal is, since we're evaluating limits, we want to massage this to look like a limit whose value we know, right? And the limits whose value, the only two really that we know for cosine and sine, are the ones we proved with the squeeze theorem, right? So you proved limit of cos x minus 1 over x as x goes to 0 is 0, and the sine one, where you squeeze the sine, we did this in session 14, this thing goes to 1. So can you see a way to split this into limits that are of this form? So we want to try to get something that involves a cosine A minus 1, and then something that involves a sine H in this thing.
Sorry, can you say the question again?
So can you see a way to split this difference quotient in blue parentheses into a sum of two terms, one of which looks like this limit, and one of which looks like this limit? Or in other words, can you split this into terms, one of which involves cosine of h minus 1, and one of them involves sine h in the numerator, all with h in the denominator? You have to do factoring in some way. Okay, maybe it's hard to see. I think probably the way to go is to notice this cosine A appears in two different terms. So it's good to factor that out. We're going to factor out a cosine.
Right before you started talking, I was like, well, if you do that, how would you deal with the sine A, sine H?
But then we can split that into a different fraction. So I'm going to take these two terms and put that in our first fraction. So that's cos h, not cos, damn it, minus 1 over h. Now, a fraction with a sum or difference of terms in the numerator can always be split into multiple fractions. So I'm just going to split this into a second fraction, factor out the sine a, well, actually the minus sine a, and then what's left? Well, what's left after I factor that out is the thing in the pink circle, which is sine h over h. Maybe the reason you didn't see that is you didn't realize that we can split a fraction like this. Is this clear why we're allowed to do this?
Yes.
Okay. Good. Okay, well, thankfully, now we can prove this limit exists because...
Wait,
well,
remind me, where did the 1 come from?
that came from this last term here. So if you factor out cosine of a from cosine of a, you're left with minus 1, right? Or said differently, if we go backwards, if we take this cosine a,
Yes.
distribute, yeah, good. Okay, so now we can prove the limit exists because this limit exists by the squeeze theorem, this limit exists by the squeeze theorem. This is a constant with respect to h, right? We're taking the limit as h goes to 0. A doesn't know about h. A and h don't talk to each other. So this is a constant. And a constant times an existent limit is an existent limit. We prove this. So this is, I've run out of space, so I will write it out more cleanly on the next slide, but this is the argument, splitting it into these two limits which exist by the squeeze theorem. Algebra questions or confusions before I show the nice clean write-up?
I have no questions.
Sweet. Okay. Here it is again. in LaTeX. Uh, Here's the definition you told me. Here's splitting it using the cosine angle addition formula, as you said. Here's breaking it into two fractions again. As I say, we've proven that both of these limits exist by the squeeze theorem. And we've also proven that if two limits exist, then you can split the limit of their sum or difference into the sum or difference of two limits and pull out constants. This one is 0, as you proved, so this whole thing goes away. The second one, well, the inside limit is 1, so this all goes to 1. And we're left with minus sine of a. Minus sine of a. So let me just emphasize this. The derivative of sine is cosine, positive. The derivative of cosine is minus sine. So they are asymmetric. When you differentiate cosine, you get a minus sign in front of the sine function. When you differentiate sine, you do not get a minus or negative sign, you just get cosine. So the slope of the tangent line to the graph of cosine x at a point x equals a is minus the sine of that same x value a. I'll show a graph with answer analysis on the next slide, but first questions on the proof, the calculation, I guess.
I do not have any questions.
Sweet, okay. That's sanity check. You should always make sure math makes sense. So the claim we're checking is it true that the slope of the tangent line to cosine of x at a is minus sine of a? Let's check some values. So the black plot is cosine. The pink plot is negative sine. So that's why a negative sign goes down to minus 1 at pi over 2. So remember, sine pi over 2 is 1, but this is minus sine. So that's why it goes downward. It's just flipping sine upside down, multiplying by minus 1. Okay, so let's see if these make sense. Let's think about x equals 0. Here, cosine of 0 has a flat tangent line, as this comment helpfully points out. A flat tangent line has slope 0, and indeed the value of minus sine at 0 is 0. Good, that's pretty easy. What if we go to pi over 2? Well, you can kind of see just by eye, the tangent line here looks like it's a 45-degree angle sloping downwards, which has a slope minus 1. And indeed, minus sine has a value of minus 1 at pi over 2. Similarly, go to pi. You see that now cosine is back to having a flat tangent line, which has slope 0, and indeed sine is 0 again. We could go over to 3 pi over 2. Now, just kind of by eye, you see the tangent line to cosine, which I've drawn poorly. It's like 45 degrees sloping upwards, which is slope 1, and minus sine has value 1, and so on and so on and so on. Hopefully this convinces you. So the argument basically goes both ways, except you need a minus sign when you use sine instead of cosine. We verified last time that the tangent line slope to sine looks like cosine. Now we see the tangent line slope to cosine looks like minus sine, just kind of graphically. Okay, thoughts and or do you find this graphical intuition convincing?
Somewhat unrelated, but remind me, was the derivative of cosine simply sine? Or wait, no, that's what we're talking about right now. Sorry.
Yeah.
Was the derivative of sine just cosine, or is it negative cosine?
Just cosine.
Okay, that's interesting.
Yeah, this is the first time we've seen a very obvious asymmetry between sine and cosine. Normally we think of sine and cosine as being more or less the same thing, except shifted by pi over 2, right? You just take one and shift it by pi over 2 to the right, so they're really the same function. Now we see there's an asymmetry in the derivatives, but the asymmetry isn't really that much of an asymmetry, because if you think about the angle addition formula for something like, I don't know, sine of x plus pi or something, I don't know, this is going to be sine x cos pi sine x cos pi plus sine pi cos x. Is that right? So cosine pi is minus 1 and sine pi is 0, so this is minus sine of x. So this isn't really the one that I wanted. I guess what I wanted was sine x plus pi over 2. This is the one that's going to go to cosine, I think. So this will be sine x cosine pi over 2, right? Okay, so this one's cosine x. So here, this is the argument I'm trying to make. If you shift sine by pi over 2, you get cosine of x. If you shift cosine by pi over 2, this is supposed to be cosine x cosine pi over 2 minus sine x sine pi over 2. So this is minus sine of x. Sorry, it took me a second to derive that because I forgot whether I wanted to add pi or pi over 2, so ignore that. Um, anyway, so the argument I'm trying to make is that you may be confused, why are the derivatives of sine and cosine asymmetric in that one of them has a minus sign and one of them has a plus sign if they're really the same function shifted by pi over 2? And I would say to you, yeah, they're the same function shifted by pi over 2, but it takes 2 pi to get back to where you started. So if you shift by pi over 2 in one of them, you're going to get plus the other one. If you shift by pi over 2 in the other one, you're going to get minus the first one. Because if you shift by pi over 2 twice, you haven't gone all the way around, you've only gone back to a minus sign. So the shifting by pi over 2, it has to have a relative sign when you go between them, because you have to do it 4 times to get back to where you started. So you shift and pick up a sign, shift, pick up a sign, do that 4 times and you get back. Um, that was not a very clear discussion, but sorry, I bungled that. But the point I'm making is that the same sign that we're seeing in the derivatives was already there in the shifts. Okay.
Okay.
Other questions?
I have no questions.
Sweet. Okay, let's use this a bit. First, I want to tell you about multiple derivatives, even though, as I say, I won't tell you about the average point interpretation until chapter 4. Okay, so if f is differentiable, the point of this slide is that we can think of that derivative, I should really say differentiable on all of r, so at every point. We can think of the derivative as a new function in its own right, because as I've stressed, we really just think of a function as a table of values that if you put in some point a, it gives you f of a, and so on. But the derivative is precisely such a table of values. I feed in, oops, that should be f prime of x. I feed in any point a, and this thing spits out the slope of the tangent line to f at that point a. So it satisfies our definition of being a function. I mean, it's a table of values and it satisfies the vertical line test because the derivative is unique, because we've proved that limits are unique. There can only be one output for each input. So the upshot of all this is that we can think of the derivative as a function in its own right because it's a table of ordered pairs. But if it's a function, we could simply ask, is that function itself differentiable? Is f prime differentiable? So we just applied the definition blindly. The definition of the second derivative, f double prime at a, it's the same definition, the same limit as it usually is, except everywhere in the usual definition we see an f, now we use an f prime. So it's the limit as h goes to 0 of f prime at a plus h minus f prime at a over h. And if that limit exists, I should emphasize, it's totally possible for a function to have a first derivative but the second derivative doesn't exist. It's very common, actually. So you can have a first derivative but not a second, you can have a second but not a third, blah, blah, blah. If that,
What is an example of this?
let's see, so how about the, yeah, let's do this. So I'll stitch together an absolute value which is 0 for x less than 0 and x squared for x positive. 0, x less than 0. Is this true? Let's see. So now the derivative of this function is going to be 0 here. Yeah, this is going to work. Okay, good. I'm glad I got that right because I was going to be embarrassed if that didn't work. Okay, so that's the original function. Now I'm going to put the derivative f prime over here, and I'm going to do it in yellow. So the derivative of a constant, yellow you can't see, blue, okay. So the derivative of the flat function at 0 is 0. The derivative of the parabola x squared we have proven is 2x. So here we stitch together the line 2x. So the derivative is a function which has a kink, right? This looks just like the absolute value plot. It's 0 over here, and it's 2x over here. So now what happens when we try to take f double prime, where I'm rapidly running out of space, but just ignore the text. Here's f double prime in gold over here. Well, it exists at some points. F double prime is 0 for negative values of x, and I'm going to draw a circle because it doesn't exist there. The derivative of the line 2x is 2, so the second derivative of this guy has a jump discontinuity, right? So we started with something which is totally continuous. We stitched together 0 and a parabola. We took a derivative. Parabola goes to 2x, 0 goes to 0. This thing has a kink. Now we differentiated the kink. This function is not second differentiable at 0 because the second derivative jumps from 0 up to 2. Discontinuous, just doesn't exist there. So this is the simplest example you can come up with, a second derivative that doesn't exist at one point. But you can probably see that I can generalize this argument and stitch together functions at many points and cook up a function whose second derivative fails to exist wherever I want it not to exist. Good. Does that answer the question? Are you satisfied?
Yep, I apologize for interrupting.
No, that was good. I wish you would do more of that. I love in talks when I get interrupted with good questions. It's much more fun. Okay, back to the flow. So thank you for emphasizing this, that we have to check whether it... So, okay, I'm going to make one more aside. I'm going to pretend you asked the following question, even though you didn't. Never mind, no. We'll talk about it later. I don't want There's a very interesting question you can ask, but I'm not going to ask it till later. Okay, so if the limit exists, we call this the second derivative. But as I say, you have to check whether it exists. Okay, fine. Makes sense. Here's a challenge. I'll ask you to work backwards. Can you find a function f with the property that the second derivative of that function is minus the original function back? Or in other words, you take two derivatives of the function, and the thing you get back is the negative of the function you started with. Think for a second.
Can we let negative f of a equal 0, or is that a given?
Oh, good. You caught me with f not equal to 0, I should have said. That is true. That is an example with this property. Because f equals 0, then, yeah. Very good, very good. I'm not being petty. That's actually exactly the sort of thinking I want you to develop, is finding these counterexamples. So you found a function 0 which satisfies what I want it to, but I'm looking for a quote-unquote non-trivial example. So non-trivial meaning not just 0. Very good. Okay. So you've answered the question. I'm actually happy. But can you find a second example which is not constant? Maybe we can brainstorm and try to think before writing it down. Let's just list the sort of functions we can differentiate and see whether each one might have this property. So we know how to differentiate polynomials with the chain rule. We can differentiate sine and cosine. We can differentiate, say, a product of two functions with the product rule, or a quotient, or a chain. Right? So first, do you think there could be any polynomial, like some x to the n or something, that satisfies this? Not constant, a non-constant polynomial.
I do not believe so. And now that I think of it, I believe that our trigonometric functions might work.
Okay, good. So let's try. Which one do you like better? Which should we try?
Perhaps we could try negative sine. Or have we not calculated that yet?
No, we differentiated sine, and we know it's linear, so you can pull out the minus one. Okay, good. So what's the derivative of minus sine?
believe that that is going to be negative. Is it going to be? I think it's going to be negative cosine.
Good, yeah. So sine goes to positive cosine, but there is an overall minus sign. So indeed, this is minus cosine of x. Good. What is the second derivative of minus sine, which is just the first derivative of minus cosine?
I believe that this is sine x.
So this is sine x. And this is exactly what we wanted, because we wanted the second derivative to be minus 1 times the original function. So indeed, if you take the original function negative sine of x and multiply it by minus 1, you get positive sine of x. So this works. As you can see, these were all red herrings. Polynomials could have never worked because if you always go down in order when you differentiate, so you could never do it twice and get back to where you started, so polynomials never could have worked. Notice we didn't even need the overall negative, right? You could have just started with f of x equals sine of x, then f prime of x is cosine of x, and f double prime is minus sine of x. So the point is, if you differentiate twice, you're always going to hit a cosine somewhere, either in the first step or the second step, and the cosine is what gives you the minus sign. So this works, sine works, or cosine works. And in fact, I will argue to you on the next slide that either sine or cosine works, first of all, because we know the derivative of sine is plus cosine. The derivative of cosine is negative sine. So if you differentiate sine twice, that's like differentiating cosine once, which gives you minus sine. And if you differentiate cosine twice, that's like differentiating minus sine once, which is minus cosine. So either sine x or cosine x works, but by linearity, we could also take any constant a times sine x plus any constant b times cosine of x, and just by applying the same argument with linearity, we're going to get back negative the original function, minus a sine x plus b cosine x and quantity. So any linear combination of them works. Good. Thoughts on this?
I have no thoughts or questions. This is cool.
Okay, good. I would like to, if you will permit me to make a slightly speculative remark on the next slide. I'm not going to actually explain why this is true, or in what sense this is true. But I've said this a couple times cryptically, but I just want to say it again. On the previous slide, we argued that the derivative, now using ddx notation, ddx of this thing a sine x plus b cosine x, the first derivative, by the way, not the second derivative, the first derivative of a sine x plus b cosine x is a cosine x, right? Because when the ddx hits the sine, that's a cosine, minus b sine x, because when the ddx hits the cosine, I get a minus sign. So this looks oddly familiar, because if we just think of this function, if you think of any function which is built out of a sum of sine and cosines, those functions have two numbers. They're totally determined by two numbers a and b. And it's very natural from what we've seen in matrices to put those two numbers a and b into a vector. So we're going to think of a function. I'm just rewriting what's already on the slide, but just for fun, I'm going to write it in pink. We think of this function as a two-component vector a and b. So all you do...
Did you intend to write cosine instead of sine there?
Thank you, thank you. Yes, interrupt me more. I like this. Good. We're going to think of this as a two-component vector. So the rule is you just take whatever the coefficient of sine is, put it in the top. Take whatever the coefficient of cosine is, put it in the bottom. Fine. Why would you do that? Well, because we've seen that the derivative mixes those two guys into one another. So the derivative df dx, which, as I've said, I'm just going to switch the order and write the sign first to make it more obvious what I'm doing. B sine x, a cosine x. I'm going to put a squiggle. It's not equal, but squiggle means related to, minus ba. So all I've done is say, think of this function as a vector. Now think of the derivative of this function as a new function, which we can still write in this vector way. by extracting the sine coefficient in the first slot and extracting the cosine coefficient in the second slot. Good. If that's true, if we can think of this way, if that's a sensible operation, then we can think of the operation of taking a derivative of a function as a map which sends two component vectors to two component vectors. It takes the vector AB, which is a sine x plus b cosine x, and sends it to the vector minus ba, which is simply a cos x minus b sine x. So in this special case of sine and cosine, we can really think of the derivative as a matrix, because a matrix, remember, is just a linear function. So this is important. We prove the derivative is linear. Linear function from R2 to R2. R2 to R2. What matrix is it in this example? Well, it's this thing, 0, minus 1, 1, 0, which, this is actually I sigma y, I think. If you remember the Pauli matrices, 0 minus I sigma y, sorry. That's not important. It's this matrix 0, minus 1, 1, 0, because doing the matrix multiplication gives us 0 times A minus 1 times B, which is minus B. And the second slot, 1 times A plus 0 times B is A. So I've told you nothing about, again, this is very speculative, so I have not proven this, but I'm just trying to slowly warm you up to the idea that it might be sensible to think of the derivative in some way as a matrix, at least in this special case. Here it happens to be a 2 by 2 matrix. You can do it in other cases where it will be a bigger, more complicated matrix. But anyway, thoughts on this?
That's me missing my push to talk key. I have no thoughts or questions.
Okay, is this slide sensible? Do you see what I'm driving at?
Yes.
Good. Okay, more. I think, yeah, finally. Okay, so here's, I usually do a preview at the beginning, or I've been trying to do a preview at the beginning with interesting stuff, so now I'm baking the preview into Act 1. So this is a very common model in chemistry for a diatomic molecule. So anything like O2, for instance, two oxygens. I'm drawing them as being connected by a spring, but I really mean not a spring, I mean the bond between them. So if you think of two atoms in a diatomic molecule, you might ask, what happens, what is the motion of these guys like if I come in and kick one of them? So if I come into this oxygen, maybe a photon bounces off and jiggles it a little bit. So if I kick one of the atoms in a diatomic molecule, how is this whole guy going to move? What is his subsequent motion? And in physics, it's very convenient to describe the motion of a system by something called a potential. And you already know this because you're reading Fundamentals of Atkins, so you know about a particle and a potential. So this is just a potential, which happens to be called the Morse potential. Morse. So what are the things in this equation? R is the radial distance between the two atoms. So the distance between the two of them is R. So if R increases, they're getting further apart. If R decreases, they're getting closer together. R appears here. So this is a function of one variable, by the way. There's a lot of letters in here, but you should think of this as just, this is a function, you plug in R, and this spits out a number with units of energy. All these other things are just constants. So d sub E is a constant with units of energy called the well depth. I'll explain why we call that in a moment. dE is the well depth. It has units of energy, joules if you like. A is a constant with units of inverse length, so this could be 1 over meters if you like, whatever. Those are the units. And of course R sub E, this is the equilibrium radius, so equilibrium radius. This just means if the two atoms are not moving, they're just sitting very calmly at whatever length they prefer to be apart, that length is R sub E, the equilibrium radius. Okay, so in the next couple slides we're going to see an example of the kind of the philosophical view I was telling you about at the end of the last meeting when you asked about very complicated equations, and I said, well, yeah, but typically in science when you have a complicated equation you simplify it with an approximation and then solve the approximation, and that's useful because you can extract a lot of interesting data from the approximate solution without doing a lot of work from the hard big equation. So I'll show you that in the next couple of slides. This will be the hard equation. We'll simplify it and then do some calculus to it. Before that, first impressions of this slide or questions about the Morse potential.
I do not have any questions.
Okay. Good. All right, so as I say, this is kind of hard to study. Why is it? Well, I mean, hopefully it's pretty clear why it's hard to study. This is a fairly complicated function. You have 1 minus some exponential, and the whole thing is squared. I mean, you can solve it on a computer if you want, but we want to actually write down a solution that we can think about. So we're going to do an approximation. What is the approximation? This is going to be an approximation for small oscillations. This is sometimes called the small angle approximation in general. Why angle? Well, I'll explain probably in chapter 9 why this is called the small angle approximation. But it's really, you should think of this as small oscillations. Small oscillations. So why do we call it small oscillations? We're going to assume that the two atoms in this diatomic molecule are close to the equilibrium distance. So lots of crazy things can happen if you separate them by a large distance r. So if you take them very far apart, eventually they're going to dissociate and they're no longer a molecule anymore. They split into two separate oxygen atoms that are weakly interacting. They're very far apart. But we're not going to consider that complicated behavior at large separations. We're going to say, yeah, well, okay, I don't care about, bombarding my oxygen with high energy particles that rips them apart. I'm just thinking about room temperature oxygen, so they're pretty close to the equilibrium distance. And the approximation we'll make is say, okay, this is the graph of V of R, by the way, that weird complicated thing I showed you on the previous slide, which is proportional to like 1 minus e to some junk squared. That's the blue curve called Morse. And the observation is to say, well, if I look at this point close to the equilibrium radius, and I'm not too far from that, this complicated graph looks an awful lot like a parabola, right? The green curve, which is labeled harmonic, it's a harmonic oscillator, small oscillations, harmonic oscillator. This green curve is a parabola which is chosen to approximate the complicated blue curve near R sub e. Right? This is the approximation. So I've written the parabola here. We're going to approximate the complicated thing, which involves e to the junk. We're going to approximate it as V of R is approximately equal to some number kappa, which I could compute for you, but I won't because it's not important. Kappa times R minus R sub e squared. And hopefully you can just kind of see if I foiled out this square, I would get some quadratic equation in R, right? This is all a function of R. So I get some quadratic, which is a parabola. The parabola is shown in green. That's the point. So in the next couple slides, we're going to study approximate solutions using this parabolic approximation near R sub e. Okay, questions on this?
Why do we have Morse?
This is named after a physicist whose last name was Morse and whose first name I have forgotten. We can Google later.
Okay.
Yeah, sorry, just some guy's name. Other questions?
I have no questions.
Not the same guy as Morse code, if that's what you were thinking. Or at least I don't think it is. Okay, here's the first challenge for you. You will need to use your differentiation rules. So, yeah, I can't tell you why this is true yet. I mean, I would have to teach you a little bit of physics. So, assume that this is Newton's second law. Newton's second law. I can't explain to you why this is true, so I will ask you to take this as given for the moment. Newton's second law is written here. Yeah. But what I will ask you to do is, if you are allowed to assume this equation is given, and we want to calculate this thing appearing on the right side, so minus the derivative of v with respect to r, where v is given by this equation, kappa times r minus r sub e squared. What is the derivative, or minus the derivative, I guess, of that function v with respect to r? And I'll emphasize again, when you differentiate, treat kappa and r sub e as constants, right? So you differentiate with respect to just r. What do you think?
So is differentiating this as simple as taking down the 2?
Yeah, but explain to me why that's all we have to do. Shouldn't we have to chain rule because there's like a thing inside or something?
We can, I think that we can act as if r minus r sub e is a single value. I don't see why we can't do that.
Yeah, so say one more thing about that. So why is it that ddr of r minus r sub e, you're saying we don't have to worry about this part. So why is that?
Because we could say x equals r minus re. I don't know. And take it the other way around.
Well,
Yeah, I didn't word that right at all.
I think the point you're getting at is that r sub e is a constant, right? So this is like the derivative of 1, right? So the derivative of a constant is 0, right? And the derivative of r with respect to r, that's just the slope of the line y equals x. This thing is 1, right? So to be totally explicit, if we were going to differentiate this thing very, very carefully and put all of the steps in, we would say, okay, we need the chain rule. So the derivative of the outside function, that's just something raised to the second power. So the derivative of the outside function is twice kappa r minus r sub e. But the chain rule says you then have to differentiate the inside function, r minus r sub e. And then, as I think you were saying, that doesn't actually matter because the derivative of r is 1, the derivative of r sub e is 0, so this whole thing we're multiplying by is 1. So we're actually done.
Yeah, that wasn't what I was thinking about.
Ah, okay.
But I was kind of skipping steps.
What was the step you were talking about?
I got to the point where I didn't understand why we couldn't just do the bring down the 2.
Couldn't understand why we could. Okay. But
Ignore me.
no, I think I see what you're saying. But is it clear now that we can't? I mean, let's make the problem slightly different. If there were a b in front of that r, if it were br inside, then we couldn't just bring down the 2 because we'd have to multiply by a b, by the chain rule, right? So is it clear why bringing down the 2 is the first step? We also need to chain rule the inside, but in this case it just so happens that that just multiplies by 1.
Yes.
Okay, good. I'm happy with this. Okay, so our answer then should be, again with an overall minus twice kappa r minus r sub e. Good, simple differentiation. Okay. Now I will promptly erase that and then write it nicely with LaTeX. Okay, so as you say, the derivative of the potential with respect to r is minus twice kappa r sub e. This is kind of annoying to write, so I'm just going to define a new variable to make life a little simpler. So I define this with the Greek letter rho. Rho is going to be this thing in parentheses, so I don't have to write that anymore. R minus r sub e. Notice that doesn't change the left side because the derivative of rho with respect to t is, well, it's the derivative with respect to t of r minus r sub e, which is the derivative of r with respect to t minus the derivative of r sub e with respect to t. What is the derivative of r sub e with respect to t?
I have no idea what just happened.
So I'm changing variables here. I just defined a new variable rho, right? Which is the thing in parentheses. Good. And
Wow. So it's going to be 0.
yeah, so r sub e is a constant, so that thing is 0, right? All I'm saying is that since this thing is 0, different color, since this thing is 0, the derivative of rho is the same as the derivative of r. Why am I saying that? I'm saying that because even though we've defined a new variable rho which changes the right-hand side because we can replace r minus r sub e by rho, it doesn't change the left side. Because if we take 2 derivatives of r with respect to t, that's the same as taking 2 derivatives of rho with respect to t. Because they differ by a constant, and the derivative of a constant is 0. Okay, so Well, even if that's not totally clear, then if not, just black box that entire discussion and focus on this equation now. So now we have a new equation. By the way, I didn't tell you this before. This is the other notation for the second derivative, right? So f double prime at x is the same as, the other notation. This is really, I think this is kind of cute, but it's also kind of shitty. So remember the notation we used in the Leibniz notation for derivatives is d dx. So you could say, what is the Leibniz notation for two derivatives acting on f? Well, it should be d dx f. And then we do the shitty thing where we pretend that these are fractions. You pretend that this is a fraction where you multiply d and d upstairs, and this is d squared. And then you pretend that on the bottom, this is just something dx squared f. And then you just don't write the parentheses. So you write a d squared over dx squared. So anyway, this isn't a fraction, and these aren't just multiplying numbers, it's just notation. So the point I'm making is that this thing on the left, if you don't like Leibniz notation, just think of this as rho double prime of t. Whatever. Okay, fine. Here's the challenge for you after all of that preamble. Several slides ago, I asked you to find a function whose second derivative was minus the function back. You told me that sines and cosines have that property. Now we have a slight variant. I'm asking you find a function rho so that when I take two derivatives of rho, I get minus some number times rho back. So if 2 kappa over m were 1, this would be the same problem we solved before. It would just be a sine or a cosine. Now it's slightly different. I'm asking you to cook up a function so that when I take two derivatives, I get this number times rho back. So I've given you a hint. Take a minute or so and see if you can think and find a function that does that. This is a typo. It should be plus. You do get a minus.
So I'm thinking, it says that we can use the chain rule, so can we say our first function is sine and our second function is going to be 2 kappa over m, and somehow get something like that? I'm thinking.
So you want to compose the function sine and 2 kappa over m times, I guess, t, since this is supposed to be a function of t? That's the plan?
I don't believe so, but if you think that works.
Well, what was your plan? This is almost right, but not quite right. What was your plan? Well, let's back up. You said use the chain rule, so we should take our first function as sine and our second function as 2 kappa over m. Maybe you meant 2 kappa over m times t and sine of x times the argument or something. Okay, so these are our two functions, right?
I'm thinking. Yeah.
Okay, so to use the chain rule, we have to compose these in some way, right? Because the chain rule will allow us to take the derivative of one of them and multiply by the derivative of the other. And as you suggested, this looks like a pretty nice function to multiply by the derivative of, because the number we're multiplying by is exactly the junk that we want to get, right? So one strategy could be to compose these in the order, well, maybe I should give them names. If this is f and this is g, one strategy is to compose them in the order f of g of t, because as you say, this will, when we take the chain rule, multiply by g prime, which is what we want. This is sine of 2 kappa m over t. Good? Okay. Let's call that rho, or it's our guess for rho. Let's just go forward with that and see what happens. What's the first derivative of this guess function rho, which I've written on the right? What's the first derivative of rho with respect to t?
I believe this will be, let me think. The loveliness of trying to remember cosine and all that, the derivatives of trigonometric functions.
Yes, you will memorize it soon enough. Sine goes to cosine, cosine goes to minus sine.
Okay, so this is going to be negative sine of 2 kappa over m.
Oh, you're taking two derivatives, or let's do one derivative first.
So what did I miss?
So you said minus sine of 2 kappa over mt, but the derivative of sine is cosine. Let's take the first derivative, right?
Oh, okay.
Okay, so then say again, since I've already forgotten, what should the first derivative be?
So I believe that this should be negative cosine of 2 kappa over m plus, excuse me, not plus. Let me think.
So multiply by the derivative of the inside, right?
Yes, times 2 kappa over m times t.
Well, the derivative of the inside with respect to t. So just 2 kappa over m, right? Right, because the derivative of the inside with respect to t, this is some number times t. This is like at, so the derivative of at with respect to t is just a, right? So there's no t on the outside. Is that too fast? Should I do that explicitly?
I don't understand that, but okay.
Well, okay, let's do it. So here, this is f of g of t, right? So here's the chain rule. Rho prime of t is, our outer function is f, right? So it's f prime of g of t times g prime of t. Now f prime, well, the derivative of sine is positive cosine, right? So positive cosine, what's g of t? I plug in g of t inside, which is 2 kappa over mt. Now I multiply by g prime of t. What is g prime of t? G prime of t is the derivative of this with respect to t. But the derivative of this with respect to t is 2 kappa over m, right? There's no t left. This is like differentiate. If it were x, this is the derivative of 2 kappa over mx with respect to x. The power rule, this is t to the first, so you bring down 1 and subtract and get a 0, right? So there's no t left.
Okay, that makes more sense.
Okay. Good, so do we agree the first derivative is twice kappa over m cosine of 2 kappa over mt?
Yes.
Good. All right, now what's the second derivative?
I believe that the second derivative, remind me, is m a constant?
Yes, I should have said that. M is the mass of one of our atoms, like the oxygen, so m is a constant.
Is kappa a constant?
Yeah, kappa was, I didn't tell you what it was. It's just a particular number that we get from approximating the Morse potential as a parabola. So both kappa and m are constants. The only thing that gets hit by the derivative is t. So prime really means d by dt. Treat everything else as a constant and only differentiate t.
So I'm inclined to believe that we are taking the derivative of 2 kappa over m, and that is going to be equal to 0.
Oh, so you're product ruling. So you say we hit this with the derivative and that's 0, and then we hit this with the derivative, or something.
I believe so, but that
Yeah,
isn't quite what we want.
that's true. We could do it that way if you think. So if you prefer, we think of this as a product of two functions. So by the product rule, this is the derivative of the first function, which is 0, times the second left alone, which I won't write because it's 0, plus, by the product rule, the first function left alone, so 2 kappa over m left alone, oops, times the derivative of the second function. Derivative of, I'm running out of space, 2 kappa over mt. Good. Okay, so by the product rule, now all we have to do is differentiate the second function, cosine 2 kappa over mt. So what's that derivative of this second piece?
So I believe that is going to be negative sine.
Yeah, negative sine of 2 kappa over mt times what? You have to chain rule the inside.
Times, wait, chain. Okay, even further thinking. Times 2km over t. Excuse me, 2km.
2k
Excuse me,
over m.
2k over m.
Yeah, good. Okay, so I'll say all those words and I'll write it down. So you say derivative of the outside is minus sine of 2 kappa over mt times the derivative of the inside, which is 2 kappa over m. Good. We already have a 2 kappa over m outside, so now there's a 2 kappa over m squared on the outside times, as you say, minus sine of 2 kappa over mt. Okay, so that's the second derivative. So now we see that our guess doesn't quite fit the bill, because we were looking for a function so that when you take two derivatives, you get minus 2 kappa over m times the function back. And the function rho that we've written down, we just took two derivatives, and instead of getting minus 2 kappa over m times the function back, we got minus 2 kappa over m quantity squared times the function back. So we got a squared instead of just 2 kappa over m. Do you see a way to fix this without redoing really any work at all? A way to fix this so that the prefactor is now 2 kappa over m instead of 2 kappa over m squared.
Is this something along the lines of, oh wait, no. I'm thinking.
Let me ask it a different way. So if this number in g, this constant in front of t, if this were some constant a, then the calculation we just did shows that if you take two derivatives, the number in front of the function with this minus sign is going to be roughly minus a squared, because you get two copies of a out. So what should a be if we want a squared to be 2 kappa over m?
At this point, I'm just guessing it's going to be the square root of 2 kappa over root m.
Yeah, so just put, I'm not even going to rewrite the whole calculation. I'm just going to put square roots over everything. So we put square root 2 kappa over m inside the sign, and then at the end of the day, this will no longer be squared. Good. So this is a very common trick. If you do a lot of physics, you won't go through this every time. You'll just memorize that if you have a harmonic oscillator, the frequency is always going to be root k over m, well, or 2k over m depending on your normalization, but it's always a root k over m. This is something I told the physics GRE students to memorize because it comes up so frequently. Good. Okay, so this slide is a mess. Let me show you one more time more cleanly and then see if there are questions. So, as we said, oh, I didn't write out the calculation very cleanly, but okay. I claim that if you take either a sine or a cosine or any combination of sine and cosines with coefficients a and b, then this function will satisfy this equation. Why is that true? Well, because rho prime of t, the first derivative by the chain rule, is a root 2 kappa over m cosine of root 2 kappa over m t minus b root 2 kappa over m times sine of root 2 kappa over m t. That's the first derivative. And now we take the second derivative over here, rho double prime. Well, by the chain rule again, I'm going to pull out a minus a times 2 kappa over m sine root 2 kappa over m t. And then again, minus b, you pull out another square root 2 kappa over m, 2 kappa over m cosine root 2 kappa over m t. So this, we've taken two derivatives, and you see by comparing this to the original expression, this is exactly minus 2 kappa over m times the original function. So we have found a function which satisfies the equation we wanted, right? It's any combination of sines and cosines. So what does this mean? Well, first, questions on the calculation. It doesn't matter if you follow all of the steps, but is the first the big picture, and two, at least the taking the derivatives part. Are those parts clear, and or are there questions?
Yes and no.
Okay. Okay, so what's the upshot of all of this? We were trying to find a physical answer for the question of how does the distance between these two oxygen atoms in a diatomic molecule change if you kick one of them. And we found roughly that if you're close to the equilibrium distance, the distance looks like a sine or a cosine. We know what the graphs of sine or cosine look like. I'll just draw sine. It kind of oscillates. So the answer we're getting out of this analysis is that if I come in and kick one of the oxygen atoms, and this is the distance r between them as a function of time, I kick one of them, then the oxygens get further apart, and then they come back and get closer together, and then they go back and get further apart, and they just kind of wiggle, which is kind of exactly what you'd expect, right? If they want to be at a particular equilibrium distance and you kick one of them to perturb their distance from that equilibrium, then they're going to kind of oscillate around it. I have a better drawing of that than the one I just did. So answer analysis. First, the claim, well, I'm going back from rho to r, but it's the same thing. You just add, it should be r sub e, but it's going to oscillate around r sub e now. So if you think of this, I would like to go to the animation. If you think of this as two particles connected by a spring, where this spring simply represents the chemical bonding between them, then you visualize our solution that we just found that involves the sine and the cosine as, the spring oscillating between, a stretched and compressed state. So you can probably guess what the animation is going to look like, but it makes me happy, so I'm going to load it up anyway, despite my computer being very slow.
I like I got like 3 sentences out before it finally loaded.
It still hasn't quite loaded. Do you see the white screen of Chrome? Also, I wanted an example where it looked like the two atoms were the same size, like O2 or N2 or something. The only example I could find is someone who simulated it for hydrogen chlorides. This is HCl, which is why the green one, the chlorine, is much larger. Here we go. Good. So, I don't know. I find this very cute. So what is this visualization showing us? Well, on the bottom is the kind of obvious motion you would expect if you kick one of the atoms. Then they're just going to oscillate back and forth between a stretched and compressed state. But the nice thing is that on the top we see what that corresponds to in terms of the Morse potential. So we approximated this near the equilibrium distance. So notice the bottom of this well is the equilibrium, and the claim is that if you kick the particle near the equilibrium, then it just kind of rolls back and forth in this potential between these two kind of maximally stretched and maximally compressed distances. And it rolls around here. And it looks roughly like a sine or a cosine. You can almost, if you tilt your head to the left and kind of just think about this, see this little the gray cursor? If you think of this as kind of going in time, you can see it traces out a sine or a cosine. So that's the point. The fact that sine and cosine have this nice property that you take two derivatives and get minus the thing back, is what makes them an unbelievably common solution in all sorts of physical and chemical applications. But okay, I could stare at that all day, but I won't. Um, Good. Okay, so that's the end of the Morse potential stuff, which is good because we have a second act to do, and like 45 minutes left. So, questions on this?
Two comments. I just got my milkshake, and also I need to plug in my laptop quick.
Okay, I will be here.
Also, your microphone suddenly changed. I don't know why. It might have been the fact that my PC is starting to die.
Well, better plug it in.
I see.
Are you enjoying that? Good. Are you plugged in?
I am.
Excellent. And your milkshake brings all the boys to the yard, as I've seen.
And I was waiting for that.
Okay, next. E to the x. Probably the most important function in analysis. So, yeah, I'm going to have to come clean about how I can't actually prove this properly, so I will alert you to the sketchiness. But I would like to make you aware of why I'm being a bit sketchy. So, it's very hard. If you look at intro calc courses and how they discuss e to the x, you will find many approaches. So the only honest way, I think, to treat this is to delay the discussion of e to the x until you have learned integrals, which is the second half. Right, so we're doing derivatives now. After that, we'll do integration, and then typically once you've done integrals, you can define the number e and what you mean by the function e to the x, and then you can prove all of its properties rigorously. That's the right, honest way to do it. And that's what Spivak does. So Spivak completely refuses to discuss exponentials in any way. He will not discuss e to the x or any function like that until defining integrals. That's a little hard for a high school class because you're expected to know exponential stuff from like a pre-calculus class, and it's very nice to connect those topics to what you talk about in calculus earlier. So a second approach that some calc books do, like the AOPS book, is they say, look, I can't prove this to you, but just believe this really crazy thing. That if you take the derivative of e to the x, it gives you the same function back, e to the x. I can't prove it, but just believe me. And then they just go on. I find both of these kind of unsatisfying. So what I'm going to do instead is a half sketchy, half proof-based, half rigorous approach. So instead of doing the correct definition of e to the x using integrals, which Spivak does, I'm going to use a temporary stopgap definition of e to the x, which is the one I told you in chapter 1. You may remember the story about the bacteria dividing. In the optional DC we had one day where I said, okay, consider bacteria that divide every day, then every 12 hours, then every hour, and compute how many of them there are at the end of the day, and as the limit as the division cycle goes to 0 time, the number of bacteria you get at the end of the day is E times the number at the beginning of the day. Um, this is, by the way, totally not kosher for many reasons. One, I haven't proven to you that this limit exists. I would need an epsilon delta argument to show that this limit even makes any sense. And I can't do that with the tools we have so far. Second, we have defined what it means to take the limit as x goes to infinity for a function f of x, which is defined on the reals. We have defined this rigorously, so that's fine. Here n is an integer index. I have not defined for you what it means. Oh, n goes to 0, n goes to infinity. I have not defined what it means for an integer index in a sequence to go to infinity. I have not defined this rigorously, and maybe we'll do it later in chapter 9 or whatever, but I haven't done it yet. So this definition is officially junk. Yeah, sorry. I mean, it's very common to present this definition in high school. The AP Calculus exam expects you to have this definition memorized, even if you don't know what it means. I haven't defined it, as I've just argued. I haven't proven the limit exists, and I haven't even defined what I mean by an integer index limit. But what I'll do is say, here's our temporary definition. It's not great. If you accept this definition, I will prove this statement for you, that the derivative of e to the x equals e to the x. And then when we get to integrals, I will retcon our definition and say, actually, that never happened. Here's the real definition of e to the x. Now everything is rigorous, and then I will go back and prove that this definition actually makes sense, and it's equivalent. It's exactly the same as the rigorous definition that we'll retcon it with. That's very sketchy, so I'm just warning you. I apologize, it's sketchy, but it's what I'm going to do. Okay, questions on the sketchiness?
I do not have any questions. I assume you need excuse me. I assume that you're going to need derivatives when you do integrals, and it's kind of catch-22.
Not really. So remember the book, the first reading we did, which was a historical introduction, and it was out of Apostle's textbook, so Tom Apostle. Apostle does integration first, so he does integrals before derivatives. So you don't actually need it, but it's untraditional to do this, to do integrals first. I think it's easier to do derivatives first and then study integrals and then see the connection between derivatives and integrals if you go in that order. But strictly speaking, no. The answer to your question is you don't, strictly speaking, need derivatives for integrals. Very good question. Other questions?
I have no other questions.
Good. What flavor is your milkshake?
Chocolate.
Oh, I think you said that, right? Okay, this is going to be kind of a lot of work, so I will show you the proofs, but if you get bogged down in the details, that's fine. First, we need an inequality. We're collecting inequalities. We have the triangle inequality. We're going to need a new one now called Bernoulli's inequality to prove this e to the x junk. Here's the theorem. Let r be any non-negative integer. So r is an integer, and here I've assumed it's greater than or equal to 0. So these are non-negative integers, 0 and the positive integers. X is any real number, but it has to be greater than or equal to -1. Those are our assumptions. Then here's the conclusion. This is true. It's kind of surprising. This is very powerful. It's true for any x and r satisfying these assumptions. If you take 1 plus x and raise it to the power r, it will always be greater than or equal to the number 1 plus r times x. So 1 plus x to the r always at least as big as 1 plus rx. How do we prove it? Okay, well, the dead giveaway is r is in the non-negative integers, so you should use induction. We'll induct on r. So remember, to induct, you prove it in a base case, and then show that if it's true for one number, like k, it's true for the next integer, k plus 1. Okay, base case. R equals 0. What happens if you take this equation and plug in r equals 0? Well, then it's just 1 plus x to the 0 is at least as big as 1 plus r times 0. So this is pretty easy to prove because the left side is 1, and, 1 plus x, r equals 0. Yeah, this is, I think I have a typo here. Yeah. 1 greater than or equal to 1. Sorry. If you plug in 0, r equals 0 gives 1 plus x to the power 0 on the left, which is 1. 1 plus 0 on the right is 1. And it's true that 1 is greater than or equal to 1. That's obviously true. So it's true in the base case. Now we induct. Assume the claim is true for some integer k. Now we have to prove it's true for k plus 1. To do that, I'm going to compute the left side of this inequality and show it's bigger than the right side when r equals k plus 1. The left side is 1 plus x to the k plus 1. By our exponent rules, you can split that into the product of 1 plus x to the power 1 times 1 plus x to the power k. Now I'm going to use our inductive hypothesis. We've assumed it's true when r equals k. So that means this factor, which is exactly the thing we know how to bound if it's true for r equals k, that factor must be greater than or equal to 1 plus kx. So that's just what I get by assuming this is true when r equals k. So in that step, we use the inductive hypothesis to say this is greater than or equal to the first thing left alone, the second thing replaced by the thing we've assumed is true in this case. Okay, now I just FOIL this out. This is 1 plus kx plus x plus kx squared. This must be greater than or equal to 1 plus kx plus x, where all I've done is dropped the kx squared. Why is it bigger than that? Well, k is an integer which is greater than or equal to 0, and x squared is positive, or non-negative at least. So this thing, I can only add a non-negative number. So if I add a non-negative number, it has to be bigger than or equal to the thing without that. So certainly kx squared is non-negative, so this thing is bigger than that. Then you simply notice on the right side one can factor. This is 1 plus x times, when I factor out, k plus 1. So when I do that, this inequality becomes 1 plus x to the k plus 1 is greater than or equal to 1 plus k plus 1 times x. And now if you look back at the thing we're trying to prove, we have just proved exactly the claim in the case r equals k plus 1. So if you take this r and replace it by k plus 1, you get this. If you take this r and replace it by k plus 1, you get that. So to summarize, we proved it's true for r equals 0. We proved whenever it's true for k, it's true for k plus 1. Therefore, it's true for all of the non-negative integers by induction. Okay, thoughts on that?
I have no thoughts or questions.
Okay. Are your algebra chops strong enough to follow all those steps?
Yes.
Good, good, good. Okay, another lemma. Now, for any x, any real number x, it is also true that e to the x is at least as big as x plus 1. This is actually, some textbooks define the number e by saying it's the unique number such that this inequality is true for all x, which I think is a very funny roundabout definition, but it's actually true that there's only one number which has that property. Anyway, how do we prove it? Okay, so I asked you to accept this supposedly nonsensical definition of e to the x. So I'm going to use that definition assuming it actually makes sense. How do we use that and Bernoulli's inequality? So we proved on the previous slide 1 plus y to the r is greater than or equal to 1 plus ry. Now I'm going to set y equals x over n, so I put that in here, and I set r equals n, so I put that in both here and here. When I make that substitution, on this side I get r times y is x over n times n, which is x, because the n's cancel downstairs. And on the left side I get 1 plus x over n to the n. Okay, so Bernoulli's inequality tells us that each of the guts of the limit, each of these things appearing inside the limit, 1 plus x over n, they are always greater than or equal to 1 plus x for all of the n's. So now we appeal to something we proved before. If one function is always strictly lower bounded by a second function, so f of x is less than or equal to g of x for all x, and the limits exist, so the limit as x goes to a of f is less than or equal to, if the limits both exist, so if the limit as x goes to a of f exists, and the limit as x goes to a of g exists, then we've proved, as part of the squeeze theorem for instance, that the limit of f at that point must be less than or equal to the limit of g at that point. Right? So this is something we proved before. So if you will accept my claim that that proof also applies for this undefined notion of integer limits, which it actually does, but I haven't proven, then we can bound the value of this limit because we know that this is a limit of a function g, which is always greater than or equal to some other function f. So that means this limit must be greater than or equal to the limit where we replace the guts of the limit by the thing which bounds them. It must be greater than or equal to this bound of the limit as n goes to infinity of 1 plus x. But now this limit's easy to evaluate because 1 and x don't know about n. They're constants with respect to n. So the limit of a constant is simply that constant, 1 plus x. And that completes the proof of this lemma that we'll need. So e to the x is always lower bounded by 1 plus x, greater than or equal to 1 plus x. Good. Questions on this?
I have no questions.
All right, lots of work, but now we can actually prove the claim. All right, this is it. This is probably the most important result of the meeting. So, theorem. If f of x is e to the x, where e to the x is defined in the sloppy way that I did several slides ago, then the derivative of f at a, f prime at some number a, is e to the a, which is to say the derivative of this function, e to the x, is the same function back, e to the x, where I've just replaced the dummy variable x with a. So you differentiate it, you get the same thing back. How do you prove it? Okay, well, we have to use the definition. So the definition of f prime at some point a is the limit as h goes to 0, e to the a plus h minus e to the a over h. That's just the definition. F of a plus h, f of a. Now I use my exponent rules here to factor out e to the a, because of course e to the a plus h is e to the a, e to the h, and e to the a, e to the h minus e to the a, you can factor out an e to the a. It's e to the h minus 1. So that's all I've done here. Inside the limit, I've factored out e to the a, and I'm left with this limit. This is the hard work, to show that this limit exists. The limit as h goes to 0 of e to the h minus 1 over h. That's hard, but we'll do it with the squeeze theorem. So what will our squeezing functions be? Well, the hint comes from our lemma and from Bernoulli's inequality. So we proved on the previous slide that e to the h is greater than or equal to 1 plus h for all h. So this is the lower bounding function for e to the h, which we'll manipulate in a moment. But e to the h is greater than or equal to 1 plus h. In particular, we prove that that's true for any number h, positive or negative. So if we replace the variable h, you simply replace in this inequality everywhere you see h, you replace it with minus h. That means e to the minus h is also greater than or equal to 1 minus h. And then e to the minus h is the same as 1 over e to the h, so you can simply invert both sides of the inequality, flip top and bottom, numerator and denominator. That reverses the direction, but it gives us a second bound. E to the h is less than or equal to 1 over 1 minus h. Okay, now I just combine those two bounds. E to the h is bigger than this, e to the h is less than or equal to this, so I put this one on the right and this one on the left. So now we have we're getting towards a squeezing bound. We want to squeeze this thing. We're getting there. We have a bound for e to the h now to squeeze that. Not quite what we want, but on the road. Okay, so questions about deriving this squeeze bound from our lemma.
I have no questions.
Good. Okay, so our next step is going to be to subtract 1 from all three of these sides. So I subtract 1 on the left. That goes away. In the middle, I'll have e to the h minus 1. On the right, I'm going to get a common denominator. So I'll do that on the next slide. Fuck. Good. Subtract 1 from all three sides. As I say, on the left, h minus 1 plus 1 is h. The 1's cancel. In the middle, we have e to the h minus 1. On the right, we have 1 over 1 minus h minus 1. We write 1 as 1 minus h over 1 minus h, get a common denominator. Then the algebra here just works out as follows. You have 1 over 1 minus h minus 1 is the same as 1 over 1 minus h minus 1 minus h over 1 minus h. 1 minus 1 minus h is plus h, and the denominator is 1 minus h. So that's just algebra. So we get h over 1 minus h on the right. Now we're taking a limit as h goes to 0, which means we can assume h is not equal to 0, because limits don't care about what happens at the point in question. Since it's non-zero, we just divide all three sides by h. Finally, there's two cases. Remember, if you divide inequalities by a positive number, the directions stay the same. If you divide inequalities by a negative number, the directions flip. But that actually doesn't matter, because both the left and right side of the inequalities are both going to tend to 1 in the limit we care about. So it actually doesn't matter whether we squeeze it between 1 below and 1 above, or 1 above and 1 below, because it's 1 in either case. Because the point is that, as h goes to 0, this thing goes to 1, and this thing goes to 1. So regardless of sign, the function in between, which is e to the h minus 1 over h, is squeezed between two functions whose limits exist, right? We prove this limit exists because it's a quotient. We prove that the quotient of continuous functions is continuous if the denominator is non-zero. Constant's obviously continuous. Limit exists, that's fine. So by the squeeze theorem, this limit exists and equals 1. So this thing goes to 1. Finally, there's the e to the a constant. So we have a constant times something whose limit is 1. That limit exists. So the whole thing is e to the a. So the punchline of this entire argument is that the derivative of e to the x is e to the x if we define e to the x the way that, in the sloppy way, e to the x equals limit as n goes to infinity, 1 plus x over n to the n. Box. Okay, so it's a lot of work. I mean, if you get the big picture of the proof and remember the important result, that's probably enough. But if you understand the proof, that's even better. So questions about the proof?
I don't have any questions.
Okay. All right. A couple slides left. This is just kind of meta commentary about other ways we could have done it. So as I've emphasized before, I haven't proved this limit exists. I haven't told you about what it means for an integer index to go to infinity. So we'll have to fix that eventually. But now is not the time. What are other ways you could do it? So in mathematics, we start with a set of definitions and axioms and try to build up everything from them. And in the approach I've just shown you, we started with this as our definition and then built up the theorem that d dx e to the x equals e to the x. We build this up from that definition. We could have made different choices. We could have made a different definition of e and still prove the same result. It would just be a different style or a different order of presentation, but it would be logically valid. So what are some other logically valid ways we could have done this, and why didn't I do it those ways? Okay, so way 1. This is I'll call this way 0. So this is way 0, the one we actually did. Way 1. You can define e to the x as this infinite sum. So you add up all of the numbers from n equals 0 to infinity. For each n, you take x to the power n and divide it by n factorial. So when n equals 0, this is 1 over 0 factorial is 1. When n equals 1, this is x to the 1 over 1 factorial, that's x. X to the 2 over 2 factorial, x to the 3 over 3 factorial, dot, dot, dot. It's a very nice definition of e to the x. Why didn't I do this? I haven't defined what it means to take an infinite sum, right? We know how to add up finitely many numbers. You can add, 100 numbers up. That's perfectly well defined. We haven't defined what it means to add up infinitely many numbers. So we'd have to do some work if we wanted to use that definition. Here's the Spivak definition, which is really the most rigorous mathematical definition. Define e to the x to be the unique number y greater than 0 such that the integral from 1 to y of dt over t equals x. Why didn't we do that? For the fairly obvious reason that I haven't defined what an integral means. So that's the one I will eventually retcon this with, but we can't do that yet. Here's another one. We actually could have done it this way. So remember we defined an exponential function as a function which is strictly increasing, strictly decreasing, or constant, and which outputs only positive numbers, and which satisfies this nice multiplicative property that f of x plus y equals f of x f of y for all x and y. So you could define the function e to the x to be the unique function, the only function, whose derivative at 0 equals 1, and who has this multiplicative property. That's a totally valid definition. It's surprising, but this imposing those two conditions uniquely picks out a single function. There's only one function that can have both of those at the same time, and that function is e to the x. So that's a good definition, but it's not very concrete, right? This is what we call a non-constructive definition, because I haven't told you how to actually compute the value of this function at any point. I mean, that's fine. As I've emphasized, a function doesn't have to be computable. This is a perfectly good definition. But when you're just starting calculus, you're used to functions that you know how to compute, so it's harder to think about non-computable functions, and people often find them a bit confusing. So this is why we did not do this definition, because it's perhaps not as down-to-earth as you would like. And a final way you could do it, some textbooks actually do this. I find this very funny. Remember that limit we were trying to compute? The one that I did all the work to do, right? We needed Bernoulli's theorem and the lemma to prove that this limit as h goes to 0 of e to the h minus 1 over h equals 1. So we did a lot of work to prove that. Some textbooks say, I don't want to do all that work, so I'm going to make that the definition. They say there's only one real number with the property that the limit as h goes to 0 of that number raised to the h power minus 1 over h equals 1. There's only one number with that property, so define e to be that number. And then they don't have to do the work of proving that that limit is true. So I find that very funny, but it's actually quite lazy, because why would you define a number by that limit? I just find that really amusing. Okay. These are the other ways. It's good to be aware of them. Eventually, I mean, you pick one as your definition, and you prove that all the others are true. So we could have gone in any order, but I picked way 0. Okay. Questions on these alternate characterizations of e to the x?
I do not have any questions.
Okay, last slide. I will show you a parallel universe, which is the universe where instead we use definition 3. If we had chosen definition 3, what would the proof that the derivative of e to the x equals e to the x look like? How would it be different in that parallel universe? So, okay. Suppose we took definition 3, which was e to the x is the unique function whose derivative at 0 equals 1, and who has this nice multiplicative property that we emphasized a lot in chapter 1 in the Art of Problem Solving book. That's our definition now in this universe. So theorem, the derivative of that function e to the x is f prime of x equals e to the x. In this universe, the proof is a bit simpler. How do we do it? Well, we write down the definition. The limit as h goes to 0, f of x plus h minus f of x over h. Now, this step is really nice, right? So since f of x plus y is f of x times f of y for all x and y, you can very neatly split that first term in the difference quotient, f of x plus h, into f of x times f of h. That's very nice. That's what we did before when we had the exponential, but now that's part of the definition. Okay. After you've done that, f of x is a constant with respect to h, so I pull that out. Now we still have to prove that this limit as h goes to 0 of f of h minus 1 over h exists. This is the thing that we did before with Bernoulli and the lemma, which was a lot of work. In this universe, that's only 2 lines. How do you do it? Well, you write h as 0 plus h, and then you use that f of 0 must be 1. Why is f of 0 must be 1? Well, you actually proved this in chapter 1. you prove that any function with this property, and which only outputs positive numbers, must have f of 0 equals 1. Why is that? Because f of 0 plus 0 has to be the same as f of 0 times f of 0, which means f of 0 squared equals f of 0. So f of 0, the only two numbers that solve this quadratic, is either 1 or 0. So if it only outputs positive numbers, then f of 0 must be 1. So that's really nice, because then we simply take this 1 in this difference quotient, which I remind you came from factoring out f of x, right? So we factored out f of x, so there's a 1 left from factoring out the f in the second term. So we replace that 1 with an f of 0, because f of 0 is the same as 1. But now we're golden, because when you've replaced that 1 with f of 0, this thing is exactly the definition of the derivative of the function, not at x, but at the other point 0, right? This is f of 0 plus h minus f of 0 over h. H goes to 0. That's the definition of f prime of 0. So you write that as f prime of 0, and finally you use the other assumption. We defined this function by its derivative at 0. F prime of 0 is 1. So using that definition, we replace f prime of 0 by 1 in this proof, and then that proves the claim. Because we were trying to prove the derivative is the same as the function itself. So the derivative, f prime of x, we have now proven to be the same as f of x. F prime of x equals f of x. Okay. So I actually like this proof better. I mean, if it weren't for the non-constructive nature of this definition, which many people find confusing, I would actually have used this instead, because I like this proof a lot better. You don't have to fuck around with inequalities and prove the Bernoulli stuff. But anyway, they're both nice. Questions or thoughts on this?
I think I prefer the alternate proof just because it seems like, I guess, more creative.
The alternate as in this one, the definition 3 one?
Correct. It just seems. I mean, they both prove the same thing, so I have no reason to prefer one over the other.
Oh, that's not true. There are plenty of reasons to prefer one proof over another. Mathematicians argue endlessly about whether one proof or the other is more elegant, is more deep, is more aesthetically appealing. So if you have the opinion that this proof is more creative, which is an opinion I agree with, this one is a much more elegant proof, and it's a much cleaner, and I would even say this is kind of a cute proof. It's only a few lines, and there's like a couple surprises. This surprise, replacing the 1 by the f of 0, that was a cute step. That's a nice little, there's a small twist. You get a smirk or a little grin when you see that step. So this is a very nice proof. The other proof using Bernoulli's inequality, I wouldn't call elegant. I would call it brute force. It works, it's true, but it requires, a lot of calculation.